Hello. First of all, thank you for showing an interest in my work. My name is Gerald Drenten, and I will talk about my work which is titled T1 weighted FLAIR ratio as a predictor for cognition in a large population cohort. Findings from the Maastricht Study. I have nothing to disclose. Myelin is a vital element for healthy brain development. Moreover, a lower myelin content has been previously found in patients with mild cognitive impairment and dementia, and furthermore, reductions in myelin are related to cognitive decline in these patients. Lifestyle factors are also known to impact the risk of developing dementia and cognitive decline. Therefore, these lifestyle factors might have an effect on the cerebral microstructure, including the myelin content. Obtaining imaging microstructural markers for early detection of cognitive decline has the potential to identify individuals at risk of developing dementia at an early stage. Therefore, the goal of this study is to assess whether the myelin content is a useful predictor of cognitive decline, and moreover, whether it is associated with lifestyle factors. For this study, we included over 4,000 participants of the Maastricht Study. The Maastricht Study is a large population cohort from the south of the Netherlands. Global cognition was assessed using an extensive neuropsychological test battery, where scores of the three domains memory, processing speed, and executive function were averaged. Lifestyle factors were summarized using the Lifestyle for Brain Health, or LIBRA index. These lifestyle factors include smoking, alcohol consumption, etc. All participants were scanned with a 3T MRI protocol, including a 3D T1 weighted image, a 3D FLAIR, and a diffusion weighted scan. The important scanning parameters are shown here on the slide. We used the T1 weighted image and the FLAIR image to calculate a proxy for the myelin content. Prior to calculating this T1 over FLAIR ratio, both images are bias corrected. Next, the intensity histogram of the T1 weighted and FLAIR images are matched to those of standard MNI images using nonlinear histogram calibration. From the diffusion data, the fractional anisotropy was calculated using the DiPi toolbox. The myelin proxy and the FA are averaged over all white matter voxels, where SAMSEG was used to segment the T1 weighted image. To compare the myelin proxy to other more common imaging markers, we also calculate a proxy for atrophy as the CSF volume normalized by the intracranial volume, a marker of lesion load, the volume of the white matter hyperintensities, and the FA, which is used as a marker of microstructural integrity. Note that the white matter hyperintensities are normalized for intracranial volume and subsequently log transformed to assure that they are normally distributed. The predictive value of the myelin proxy was assessed using a linear regression model, where cognition is predicted from the T1 weighted FLAIR ratio. This model is corrected for the effects of age, sex, and education level. Performance of this model was estimated using the R-squared and the t-test statistic of the predictor, in this case the T1 weighted over FLAIR ratio. Similar models were created for the markers of atrophy, lesion burden, and microstructural integrity, and significance of the myelin proxy was tested using bootstrapping. Next, the association of different tissue characteristics with lifestyle factors was assessed using linear regression models, where the MRI tissue characteristics are predicted from the LIBRA score, corrected for age, sex, and education level. The T1 weighted image, the FLAIR, the myelin proxy, and the fractional anisotropy are shown here for a representative subject. When assessing the correlation between the tissue markers, we see that all these tissue markers are significantly correlated to each other, albeit with modest correlation coefficients. Noteworthy is the correlation between the lesion load and the myelin proxy, which shows a relatively high correlation. The regression models predict cognition. The regression models predicting cognition show that for all variables, the tissue markers contribute significantly. Furthermore, the t-statistic of the myelin proxy is the highest, and this model is also showing the highest R-squared value. By bootstrapping the t-statistics for atrophy, lesion load, and fractional anisotropy, we can determine a distribution and confidence interval of these t-statistics. And the t-statistic of the myelin proxy can now be tested statistically against this distribution. And this shows that the myelin proxy is significantly better predictor than atrophy and fractional anisotropy. Furthermore, a trend towards a significantly higher t-statistic of the myelin proxy compared to the lesion burden was reported with a p-value of 0.08. Predicting the myelin proxy from the Libra scores using linear regression resulted in a model with an R-squared value of 0.45. Furthermore, the t-statistic of the Libra score was almost minus 20. Comparing these values to the other tissue markers showed that the model with the T1 FLAIR ratio explains the most variance and also has the highest absolute t-statistics by more than a factor of 2. In our work, we used the ratio of T1 weighted and T2 weighted intensities to calculate a proxy for the myelin content. This method was previously shown to improve the myelin contrast in these images. Our results show that this proxy value is a good predictor of cognitive decline and outperforms other imaging markers such as atrophy, lesion load, and fractional anisotropy. Furthermore, lifestyle factors are related to changes in the myelin content, indicating that our lifestyle has an impact on the cerebral myelination. This relation, where the lifestyle factor alters the myelin content, which in turn impacts cognition, provides new insights into the progression of the disease as well as presenting new strategies for prevention. Thank you for your attention, and if you have any questions regarding this work, I would be very happy to answer them.